Today, a chemist can be proud of because from about 10 petrochemical products which are abundantly available, what we call as natural feedstock, today we are able to make millions of compounds ranging from drugs to dyes. This advancement was possible largely due to development of organic chemistry, and in particular the ability of the synthetic chemist to modify the structures via newer CC bond formation. The majority of these reactions involve the carbanion intermediate. We all are familiar with the factors which stabilizes carbanions. In this session, we are going to discuss about one of the most versatile carbanion intermediate, namely enolate, with their utility in various CC bond formation being the central issue of the discussion. The process whereby the hydrogen atom attached to the carbon atom of a carbonyl compound moves to the carbonyl oxygen atom is known as enolization or enoketotautomerism. The isomeric carbonyl and enol structures are tautomers. The extent of enolization depends on the acidity of the hydrogen atom, that is the acidity of the proton. More acidic the proton, the more probable the enolization, and hence the equilibrium constant for tautomerism will be high. So the equilibrium constant for tautomerism is nothing but the ratio of the molar concentration of the enol to the molar concentration of the carbonyl group. Normally, the carbonyl form is favored. The structure of the carbonyl and the enol can significantly affect this KT. One more point you have to remember is this interconversion between the keto and enol form is catalyzed by both acid as well as the bases. In aqueous acid, rapid protonation of carbonyl group happens first, which is followed by removal of alpha proton by water in the rate controlling step leading to enol. Under basic condition, the abstraction of alpha hydrogen atom is the initial rate controlling step. Then the proton abstraction from the solvent completes the enolization process. And as can be seen, these processes are essentially acid-base reactions and involve many equilibriums. And the points to be noted over here is this is what we call enols, and this is what we call enolate. And of course, enolate, if you take carbonyl compound as a Bronsted acid, of course this carbonyl compound is more acidic when it is compared to hydrocarbon analogous. Enolate anion is the conjugate base of carbonyl compounds, and this enolate is resonance stabilized. It can also act as a nucleophile. This in fact is the base of their reactivity in variety of the reactions ranging from alkylation, Aldol reaction to more complex iodoform reactions. So there is one more question that we need to understand the answer. How to decide what base could be used for deprotonation of a given proton under certain conditions? A general idea of pKa values of various carbon acids will help us in understanding the reactions what we are going to discuss better, and will also allow us to decide what base could be used for deprotonation of a given proton under certain conditions. For example, one can use diisopropylamine and the pK of its conjugate acid is 36 for the deprotonation of acetone. For that the pKa value is 26.5 in such a way that the equilibrium will be almost exclusively towards enolates. We call this as deprotonation under kinetic conditions. Means this is in place of diisopropyl bromide and this is in place of acetone. It is in fact acetone only. So what happens? The base will absorb a proton and you get enolate, and the enolate is resonance stabilized. And one more factor that we need to keep in mind before we go further is, look at the table what I have shown. Can we use lithium butyl or lithium methane, that means Bu minus or Me minus or CH3 minus, to deprotonate this acetone? Ideally speaking, yes, provided we take only the basicity into account. pKa of the conjugate acid is more than that of the proton to be abstracted. However, one more aspect we have to worry about this is nucleophilicity. So if you take this, it is supposed to be written MELI or BULI, is also a good nucleophile like Grignard reagent. So they are not typically used for deprotonation, but rather non-nucleophilic bulky LDA, that is lithium diisopropylamide or LiHMDS, that means lithium hexamethyl disilazide, are used more often. We have to look at the CO as well, I mean the carbonyl part as well. Due to the polarization of this CO bond, it can act as an electrophile at the carbon center, here at the carbon center, or it can be here it could be an electrophile at the carbon center so that the nucleophile can attack over here, or as a nucleophile, or it could be a base. We have discussed what is the difference between a nucleophile and a base. A base donate its pair of electron to a proton, whereas a nucleophile donate its pair of electron to a carbon. So it can act as a nucleophile as well as a base, because these two species are excess of electrons through the oxygen atom, because this oxygen is having a two pairs of electron, or the alpha carbon sender. Alpha carbon sender means here this pair of electron can attract this electrophile, and this pair of electron can attract this electrophile. So please understand, we have to look at the carbonyl part also. It can act as an electrophile at the carbon center and also as a nucleophile at through the oxygen atom or the alpha carbon atom. And in fact, the generation of the enolates of ketones is at times challenging because they pose a problem in the regioselectivity. Ketones can have enolizable protons on both the sides of the carbonyl group. The problem is not so much complicated when one side of the ketone does not have an enolizable proton, for example acetophenone, or the ketone is symmetrical, for example 3-pentanone. The real issue is with the unsymmetrical ketone where the enolizable protons are present on either side. For the successful reaction, we need to control which side enolate is getting formed. So this side could be one, and if you take this compound, this side is more feasible. And here we could understand that if one of the two proton is significantly more acidic, the selective enolate formation is straightforward. There is no ambiguity. For example, in the case of ethyl acetoacetate, there are two types of enolizable protons. However, only one of the two proton is deprotonated first. This is an example of thermodynamic control. Only the more stable of the two possible enolates is formed, and this is less stable because this proton is having more acidity. Note the term, this is an example of thermodynamic control. Take an example of 2-methyl cyclohexanone. Where the difference in acidity of the proton on either side is not pronounced. There are two enolates. Which are possible as shown. Now, enols and enolates are alkenes, and hence the more substituted it is, the more stable it will be. Please recall Stasov rule. So, when the equilibrium is possible, the more stable enolate will form. This is possible if a proton source is available. So, remember, when equilibrium is possible, the more stable enolate will form. This is possible if a proton source is available. So, remember, this is supposed to be the more stable one. But compare the situation where we use a strong, bulky base such as LDA. LDA is too hindered and attack the least hindered CH bond alpha to the carbonyl group. Here, alpha to the carbonyl group. It also prefers to attack more acidic CH bond, and the CH bond on less substituted carbon are indeed more acidic. Also, the statistics help with more protons present on the less substituted carbon atom. So, all these factors combine and ensure that we form less substituted enolate. Less substituted enolate as the major product, provided we do not allow the equilibrium to be attained, which will lead to the formation of more stable enolate. This can be accomplished by controlling a few things. Temperature is typically maintained at -78 degrees Celsius. The reaction times are typically short, and using excess of base compared to ketone at all the time, which can be easily achieved by adding ketone drop by drop. This enolate, which is formed faster, is kinetic enolate. So if you were listening, you would have little understood what is a thermodynamic enolate and what is a kinetic enolate. This is kinetic enolate and this is thermodynamic enolate, which is not formed. Let's discuss about a few of the reactions of enolates. Enolates are nucleophiles and this can be reacted with a variety of electrophiles. Depending on the type of electrophile used, we have different classes of reactions like Aldol reaction, Claisen condensation, Dickmann cyclization, alkylation of enolates, that means active methylene compounds, Mikhail addition, and Robinson's annulation. Out of this, 3 are there in our syllabus. Let us look into the most important enolate related reaction, that is Aldol reaction. Consider the reaction of acetaldehyde with a base like NaOH. As we have discussed earlier, under basic condition, it will form enolates. Based on pKa, you will realize that the formation of enolate is not going to be complete. That means hydroxide is not strong enough to be a base to ensure complete deprotonation, and the equilibrium would largely be towards the aldehyde and sodium hydroxide. Thus, only a small amount of the nucleophilic enolate is formed. The enolate thus formed will react with acetaldehyde molecule, which is not enolized to form alkoxide. This alkoxide will be protonated by the water, which was initially formed in the first step. The product of this step is the compound which contain an aldehyde, so ald, as well as the hydroxyl group, so all. So the common name is Aldol. The name Aldol, however, is used for the whole class of the reaction involving the enolate and carbonyl compounds. Notice that the base catalyst, that is hydroxide ion, is regenerated in the last step. So this indeed is a catalyst process. In general, in this reaction, the concentration of the base has to be controlled. With a higher concentration, dehydration of aldol products occurs rather readily due to the formation of stable conjugated unsaturated carbonyl compounds. Aldol reaction turning to aldol condensation by the elimination, which is an example of a typical E1CB reaction. What is to be noted is 2 molecules of this plus this give this compound through the formation of enolates. So here enolates is the nucleophile. So interestingly, if these two reactant can give this product, what will happen? What will happen for these two reactants? So here the alpha carbon of one nitrile molecule is added to the cyanide carbon of another. So you will be getting this as the product. This reaction is what we call Thorpe reaction. So in Thorpe reaction, the alpha carbon of one nitrile molecule is added to the cyanide carbon of another. So this reaction is analogous to Aldol reaction. As expected, the CNH bond could be hydrolyzed. So beta keto nitriles can be prepared in this manner. So it will be this could be prepared in this manner. Another one of the most celebrated enolate related reaction is Claisen condensation reaction. But surprisingly, here you can't see aldehydes or ketones, instead of that esters are there. So enolate generation and further reactions are not limited to ketones or aldehyde. Even protons alpha to the ester functional group are acidic enough and can be deprotonated with a base to form enolates. These enolates are nucleophilic and can react with a variety of electrophiles. Incidentally, here the carbonyl of ester can itself act as an electrophile. Thus, ethyl acetate, when reacted with the sodium ethoxide, leads to the formation of a beta keto ester, namely ethyl acetoacetate. This reaction is known as Claisen condensation reaction or Claisen reaction. Actually, Claisen condensation involves a series of equilibria which illustrate the mechanism. So you have an in-class question, that is, you need to find out what is the mechanism of Claisen condensation reaction.